During this lecture, you will learn about exponential growth. We're going to discuss three formulas. Two of them deal with exponential growth that's positive, and one of those deals with exponential growth that is negative, which is called half-life. So there's three formulas that you'll be using on your test and on your homework. One's called the doubling time formula, and you see it right on your screen there. And one way to think about growth is how long does it take for a population to double. So this formula right here is your doubling time formula, and it tells you right down here what each variable stands for. A is what we're looking for, the population at a specific time. This is pronounced A naught. In other words, A subscript 0 is pronounced A naught, and that's your population at time t equals 0. D is your doubling time, and then T right here, this T stands for your time. So it might be time in days, it might be time in years, it might be time in minutes. It depends on what the problem deals with. So let's take a look at our first example of a population doubling. If you read what it says here, Mexico has a population of around 100 million people, and it's estimated the population will double in 21 years. So its doubling rate is 21 years. If population growth continues at the same rate, what will be the population 15 years from now, 30 years from now? Well, common sense tells us that in 15 years from now, if the doubling rate's every 21 years, it's not going to quite double yet, is it? So what we're going to do is use this formula. So we're going to find the amount of people in Mexico at 15 years from now. So the amount is going to be A naught, which is 100 million. That's the population now. And I'm just going to put 100 there, not 100 million, and then our answer will be in millions, times 2. And the reason the base of our power is 2 is because we're discussing doubling time, times 2 to the power of t over d. Well, t is our time, which is 15, and d is our doubling rate, which is 21. So we're going to grab our calculator and take 100 times 2 to the power of 15 over 21. So we're going to take 100 times 2 to the power of, so I'm going to go to the caret button right there, of 15 divided by 21, and I'm going to put that in parentheses, 15 divided by 21, to make sure that we're using order of operations here. So 100 times 2 to the power of 15 divided by 21 gives us 164.07 if I round. 164.07. And remember, this is in million. So we have about 164.07 million people in Mexico 15 years from now, would be the prediction. How about 30 years from now? Well, if the doubling time is 21 years, then it's going to be more than 200 million, because it is going to double after 21 years, plus there's going to be more people between the 21st and 30 years. So let's see what we get for the population in 30 years. We'd still have 100 as our A naught. We still use 2 as our base because it's doubling time, but instead of 15 over 21, we have 30 over 21 because our time is 30. Let's go back to our calculator. I don't know if you know you could do this with your graphing calculators, but you can hit second, enter, and that brings up your last entry. And now I'm going to edit that last entry and just change this 15 to a 30. And we have 269, about 269.2 million. Whoops, sorry about that, hit the wrong button. 269.2 million people in about 30 years. So those are the predictions for the population of Mexico if the doubling rate stayed at 21 years. Another way of looking at growth rates or population growth rate is called relative growth rate. This is another exponential growth, and it's a positive exponential growth. It might deal with people or maybe a virus spreading. growth of money at a continuous compound interest, and you've seen that one before in chapter 8. But this is the formula we use for relative growth rate. We still have A is the population times T, A naught still the population at time T equals 0. Now we have K, this constant right here. That K is your relative growth rate, and once again T is going to be your time. So this deals with population growth of the world. In the year 2000, the relative growth rate of the world's population was about 1.4%. The population of the world was about 6 billion people in the year 2000. If the growth rate remains at 1.4%, what will be the approximate population of the world in 2020? So let's fill in the blanks on this. Our A naught is 6 billion. I'm just going to put a 6 there because we'll know our answer's in billion. The time, if it's 2000, the year we start, and we want to know the population in 2020, then 20 years has passed in that time. And K is 1.4%, but we don't want to put 1.4% in for K. We want to put in 0.014, similar to what we did last module when we were dealing with compounded interest. So when we use a formula, we're going to get A equals 6 is my A naught times E to the power of 0.014 times 20. All right, let's see what the world's population will be in 2020 if the relative growth rate stays at this pace. So we had 6 times E to the power of 0.014, and I can't remember if I put that on the screen. I might have to go back and change it. I think I put 1.4. I'll have to see. 0.014 times 20. And it looks like we're going to be at about 7.94, approximately 7.94 billion people in 20 years. And I guess I was worried I'd put 1.4 there instead of 0.014. So don't forget to change your percent to a decimal when you use this formula. Okay, the last exponential growth model we're going to look at is a negative exponential growth, and it's called half-life. And you can see the formula for half-life here. And I prefer to use 0.5 instead of 1/2 when I'm dealing with a calculator, but they both mean the same thing. And half-life, you maybe have heard of half-life with radioactive materials. Half-life means how long does it take for a specific material to decay down to half of what it was originally. So how long does it take for 100 milligrams to go to 50 milligrams, or 200 pounds to go to 100 pounds, etc. So this is the formula we're going to use. And I think everything's self-explanatory. This H right here stands for the half-life. So take a look at this problem, and I think this is straight from the book. We have a radioactive isotope. It's called gallium-67. It's used in the diagnosis of malignant tumors. It has a biological half-life of 46.5 hours. If we start with 100 milligrams of the isotope, how many milligrams will be left after a week? Okay, well, we see that we're starting with 100 milligrams, so that's my 8. My A naught is 100. My time, well, let's go down to half-life. Since they gave half-life in hours, 46.5 hours, then I have to make sure my time is in hours, but we said after a week. So 1 week is 7 days, and then I have to take 7 times 24, and I don't even have a pencil on me, so I'm going to do it right here. 7 times 24, I think that's 168. Okay, it is 168. So our time is 168 hours. We have to make sure that our half-life and our time is in the same units of measure. So here we go. The amount we have is going to be 100 times a half, which is 0.5, to the power of 168 divided by 46.5. Now remember, this is decaying, it's not growing, so the amount's going to be smaller. And I got to remember these numbers as I go here. 100 times 0.5 to the power of, I believe I had 168 divided by 48.5. Oops. Since I didn't put a parenthesis originally, I'll get rid of that one. Okay. So that 100 goes down to about 9.06. So instead of having 100 milligrams, about 2 days later, 46.5 hours, we're down to 9.06 milligrams. Okay, one more example of half-life. This one's dealing with iodine 131. If 10 milligrams of iodine 131 is given to a patient, how much is left after 30 days? And it tells you there that the half-life is 8 days. So we're simply going to go and use this formula. A equals, we started with 10 milligrams, times 0.5. The time is 30 days, the half-life is 8 days, and you'd simply put that into your calculator and let your calculator do the work on that one as well. So I hope you understand exponential growth a little bit better, and especially with these 3 different types of exponential growth. Goodbye.